Welcome to the Swayam Prabha series in computer science. In the series, this is a course on artificial intelligence, and in this course we are in unit 5 on natural language processing. And since last few classes we are dealing with natural language processing, and last class about statistical natural language processing. In continuation with the last class where I stopped with TF-IDF, today we will be seeing the cosine similarity, where two documents or two words or two sentences, how to find the similarity between each other. And then the introduction to embeddings. Embeddings are how we convert a meaningful representation of words into some kind of numbers, so that that can be fed into machines for understanding. So that we will see today. At the bird's eye view, where we are is, we are at this stage like I explained during last class, and we are at this level solving NLP task, where before modern neural NLP we have to represent into some kind of the numbers. So here after TF-IDF we are going to see the cosine similarity first, and then we will move into neural NLP. But before moving into NLP, we would see the embedding structure, where we will convert into meaningful representation of words. Now we will see how we calculate the similarity between any two words or any two documents. Suppose document D1 has tea, coffee, sugar, just three, just for our understanding, and because this is a simple class, we are only finding out how a cosine similarity is calculated. Like with this handy example, you can extend it to any number, like you can even code it and check with the huge documents with respect to document similarity. Okay. Suppose you have D2 as tea, coffee, milk, and if you see these two documents, tea, there is one commonality, coffee is another commonality, the one that is different is sugar and milk. So how similar are D1 and D2? Because there are two words that are similar in both documents, we would say yes, it is similar, somewhat similar, it is mostly similar. Like numerically, how will we calculate this similarity is through the cosine similarity formula, like A dot B, this is the dot product. A is going to be with respect to the document D1, B is going to be the document D2, and A dot B, it is going to be the vector dot product of D1 and D2 divided by, this is modulus A, mod A, where it is going to be root of the vector, square root of the sum of the square of the vector, and B, this is root of the sum of the square of the vector of B, which is in D2. And if we calculate this cos theta, we would be able to find how similar it is. So let's take an example, and for finding out, we can take the one-hot encoding, which I did in the last class. So if we take one-hot encoding of 4 words, here we are seeing the vocabulary consists of unique words from D1 and D2, that is tea, coffee, sugar and milk, 4 words. And with D1, assume that how is this calculated, how do we get 1101? Because D1, if from D1 we have tea, wherever that word is present, we are giving a value of 1, and coffee is present in D1, so it is 1. Milk is not present, therefore 0, and sugar is 1, 1. So 1101 is given in D1. And similarly for D2, tea is given 1, coffee is there in D2 1, milk is there 1, and sugar it is 0, therefore D2 is 1110. Now given these terms, D1 and D2, this is a vector and this is a vector, this is vector A and D2 is vector B. So calculating D1 dot D2, A dot B, that is 1 dot 1, and this is 1 dot 1, and 0 dot 1 it is 0, and 1 dot 0 it is 0, by square root of 1 squared plus 1 squared plus 1 squared, that is 3, and square root of 1 square plus 1 square plus 1 square, it is 3, which is the denominator here. So, we would get 2 by 3, which is 0.67. So, the answer is how similar are D1 and D2? We can say it is 67% it is similar, or 0.67 it is similar. Now, another point that we can make is, suppose what is the cosine similarity of, suppose I have a D1 document as T, suppose we say T, and another also as T, D2 as T, T, T. Both documents are similar. So, what would happen to this dot product? Cos theta, it is going to be equal to 1. 1 plus, because everything is going to be 1. So, 1 divided by root of 3 and 3. So, 3 by 3, it is going to be 1. So, when it is most similar, cos theta is going to be 1, and it is least similar. Suppose we take D1 as tea, coffee and milk. Another case would be water, glass and pen. All the three words here and here are dissimilar, it is not the same. So, your vocabulary would consist of more number of words, and in this case if you take, the cosine similarity is going to be 0. So, when it is dissimilar, cos theta is going to be 0. So, the value is going to run between 0 and 1, where towards 1 it is most similar and towards 0 it is least similar. So, this is a part that we have to understand, and this cosine similarity used in multiple cases. Let us see a few places where this is being used. It is again used in search engines, document retrieval, recommendation systems, chatbots, semantic search, plagiarism and embedding similarity. A few of it we will be discussing in this course, and that is good how to calculate the similarity between the documents, but still it again depends upon the sparse vectors. Why? Because we said we will be converting into 1-hot encoding, and you can see the vocabulary size. So, that would in many places there are zeros, so that would lead to sparse vectors, and again here it is exact word overlap is required. So, if T is there in the other document, T should also be there. So, that similarity is depending on the exact word. So, again these are some of the limitations, but combining TF-IDF and cosine similarity, there are certain advantages. Let us take this example, the same example that we did before, where tea is healthy, tea is popular and coffee is strong. Take these 3 examples, and from 3 examples this is the vocabulary that we have. We have around 4, 5, 6 words, 4, 5, 6 words, and for the 6 words, suppose assuming that the TF-IDF vector we have calculated, it comes to these values. These values may be different. This is only for representational purpose. Assume that D1 has 0.20, 0.5, 0, 0, 0, which means 0.2 is for T and 0.5 is for healthy. So, this represents 1, 2, 3, 4, 5, 6 positions. And if you see document D2, T is popular, T is 0.2 and popular 4, it is 0.5, and D3 coffee is strong, second coffee is 0.5 and strong it is 0.5, and if you see the rest of the portions are all 0 according to TF-IDF. So, this is the first position where we did TF-IDF. Now, from this representation, if we are able to calculate the cosine similarity between these 2 documents, T is healthy and T is popular, if we calculate the similarity, it is 0.138. You can check the similarity using the same formula, A dot B by mod A and mod B. If you calculate it, you will get 0.138. The advantage here is we are not taking ease with respect to the similarity between these two documents, because in TF-IDF that ease is disregarded. This ease value, it is going to be 0 here. So that value is not accounted in this example, this similarity case. So this, when we combine TF-IDF and cosine similarity, we are only checking up one with the important terms and removing of the non-relevant words. So it again, what I said is given here, it removes the importance of common words. Common words in this case is, so that is removed. Cosine similarity, it directly measures the similarity, directional similarity, in the sense if it is 0.5 and this also is 0.5, if it is towards the same direction, it measures the similarity. So together they emphasize meaningful overlap and they ignore the document size. So this is a one good example of how we can combine TF-IDF and cosine. But raw counts increase false similarity. Like I said, if you have ease also, it would say that the document that's more similar, but in essence that ease does not constitute towards any meaning. So combining this TF-IDF and cosine similarity applications, it is used in search engines, again document retrieval, and document retrieval with document extraction, information extraction also is being used, recommendation system, chatbots and duplicate detection, and semantic search with respect to classical NLP, and this semantic search will be used delineated in the next few sessions. The limitations, suppose we take an example here, car and automobile. In a corpus, both terms may appear unrelated because both are not according to the vector size, each one will have a vector of 1 or 0 that will constitute 0, and because there is not overlapping, although we feel it is related, the similarity, cosine similarity will give it as 0. So this motivates word embeddings where the semantically similar word get nearby vectors. So far we have seen only the actual word, the exact word, if it is overlapping then it accounts to some value, but how do we encounter, suppose car and automobile also related, it is related by 0.6 or 0.5. So how do we do that? That by means of word embeddings. So that word embeddings, it is now we are going to shift into the neural type of NLP where we are mapping into the recent LLM features like ChatGPT, how it is built, and it is built using the transformers, and from the transformers it is actually a neural network model based where the feeding all the input would be in the form of numbers, and those numbers come from embeddings. So that embeddings is what we are going to see now. So this is a transition from classical NLP, which consists of the syntax and semantics, a little bit of semantics that we saw, and then the statistical NLP that we saw with respect to the probabilistic type, then the sparse vector representation, it is one hot encoding that we saw, and now we are going to move into the neural type of NLP with respect to the embeddings. So with the previous representation, what was the problem? Suppose we have car and automobile, it is actually synonym, and when we pass car and automobile to cosine similarity, the value would be 0, although we know that it is similar. Suppose happy and joyful, they are synonyms. In cosine similarity or in other representation, there is no relationship. Paris, France, this is a capital of a country. These are treated as unrelated tokens, but as humans we understand, yes, Paris is a capital of France. And suppose we saw in a document these three words, run, ran and running. These are the morphological variants of run and running. we understand it. But when we convert that into one hot encoding or into other types, these are considered as three separate vectors. This will not be constituted as one single vector or related to each other. And suppose we have two terms like apple, apple. This is polysemy where we saw in the semantic NLP type. Apple is a fruit and apple is a company. This actually is two different things. But when we give, it will in the one hot encoding, it will give us the same vector, although we know these are two different vectors. So these are problems, some of the problems with respect to the previous representation that we have. Now, in the traditional method, TF-IDF and cosine similarity cannot capture this relation. King is man and women, can it be equated to queen, can be similar to queen, can we have as a cluster this together. This is a very famous example that comes in actually word to vector. Word to vector is one embedding type. And again, as I mentioned, suppose we have Paris is to France, can we have Italy to Rome, can we cluster these as one type. And fast, faster or slow, slower, if we have this type as fast, faster, can we have one type as slow, slower. Those we cannot do with TF-IDF or with cosine similarity. So again, an automobile repair, just if we give it in search engine in earlier days, it would not match the document as car repair because it would identify only automobile as an automobile and not as a car. So with all these problems, embeddings can address these type of issues where it can capture the similarity based meanings. Like suppose we have king and man as some vector, women and queen would be seen related to these as a vector. So those type of numerical representation can be seen in embeddings, and one of the embedding type is called word to vec. It was done by Google earlier, and we would see this representation in this session. So what are word embeddings? This is the definition. It is a dense. Dense is of fixed size. Sparse is where we saw many zeros in the matrix. Dense, it is not actually many zeros, there are only some values and all those values have some meaning towards it. Low dimensional, because we are accounting only the values that are important. And continuous vector representation of words which are learned from data. This is very important because these embeddings are going to be learned from enormous amount of data, particularly we would be using neural network, where semantic and syntactic similarity is reflected by geometric proximity in vector space. So what we will do is we will have a vector space. The vector space will consist of the terms like a kingdom. Like if you take the previous example here, the first is the vector space would be the kingdom, where in the kingdom the vector space specifically king, man and women, queen will be there. Those will occupy a relative space close to each other. And this sector, the vector space would be the country's vector space, and here it would be the say other vocabulary like the adverb vector space or the fastness vector space, where these words, the vector values are close to each other. That is called as a geometric proximity, but we will do some examples so that you will be clear about it. Yeah, these are the two examples that represents king as a sparse vector using one hot encoding that we did before. If we just use only one hot encoding, you can see that at only one place there will be 1 and all the other places it is 0. So it can be approximated 10,000 dimensions and with mostly zeros, that is sparse, that is with respect to the earlier representation. With queen, similarly there is at one place it is 1 and all the other places are 0. And if you see, it is completely different position that it would have. Though these two are completely different. If you take the geometric proximity, it is different. But after embedding type. Assume that we will go through how embeddings are done in the next session, but assume that after embeddings are done, we will have vectors like this. You can compare the vector size here and here. This is of 10,000 dimensions, and if you see, this is of 3 dimension size, and for king it is 0.25 minus 0.61 and 0.88. For queen, assume that we have the vector of 0.27 minus 0.58 and 0.90. And how do we see both? This is close to each other, 0.25 with 0.27, it is very close, and this is of the same direction. If you see minus 0.61 and minus 0.58, it is the same direction, and 0.88 and 0.90, it is very close. So using this vector structure, we can say that yes, king is related to queen. And what about monarch? And all the 3 are going to be in the kingdom vector space. In the kingdom vector space. And the monarch, if you see, all these 3 are related, 0.25, 0.27 and 0.24. And the direction, the second position, minus 0.61, minus 0.58 and minus 0.63. All the 3 are related, pointing towards one direction. And here also 0.88, 0.90 and 0.85. All the 3 are close to each other. Therefore, we can say that this is going to be in the kingdom vector space or related. And even the semantically, we can see the mapping. Another example here is, this is the same definition that I gave before, so I am just skipping it. This sparse representation with vocabulary size as 5. If you see the vocabulary size, there are 5 words, and if you see in one hot encoding, cat can be termed to 1 and all the other things as 0. But imagine it with 50,000 dimensions. You will have 50,000 vectors like this, but only one position has 1 and all the terms are 0. And what will happen to dense embedding? It is only with the dimensions of 3, and with 3 cat is 0.82 minus 0.34 and 0.19. Assume that we have this vector numbers here. How we got this? That we will be doing in the next session. Dog, it is 0.79 minus 0.31 and 0.22, and mouse it is 0.45 and minus 0.12 and 0.67. Assuming that these are the vector values that we got after embeddings, you can see that these are related. The first vector position, the second is pointing towards another direction, and the third 0.19 and 0.22 are related, and 0.67 is somewhat less similar. So using this, we can say that okay, cat and dog are similar with respect to these vector sizes. One method to capture is word to vec. It was given by Google, and there are the types of semantic similarity that is captured. It can capture both semantic as well as syntactic similarity. Examples of semantic similarity is happy, joyful, cheerful, all can contribute towards one vector space. It can capture computer, laptop, PC, or doctor, physician, surgeon. The syntactic similarity that was having problems with cosine or TF-IDF, here we can have a similar vectors like run, ran, running. These can have similar vectors because adjective is closer to fast than to quickly. Analogical, king, man and women, queen, these can be captured using word to vec. And similarly the countries, we found it difficult using the other type of representation. Here we can capture it. Some examples of words in a general vector space. Let us take the first example here. The sparse in case of TF-IDF, we would get 0, 0, then 0 and 0.3, where 0 is accounting for the most common terms, and 0.3 is some word which is important. And if you see, there are 99.9% zeros, and that happens in the case of cosine similarity also. And if you take the after embedding, in this compared with TF-IDF and here, there are some numbers with the vector as a vector, with some values of minus which indicates the direction, and when we compare the earlier one with this, the dense embedding, the number of values are less, the dimension is less, and these values all represent some meaning with respect to the vector space. And the benefit is the efficient storage because of the size, better generalization. Say when we consider as a previous example of cat and dog, we can say that both are pet animals, and it also captured the relationship between the two vectors. Say for example, king and man, queen and women. Words that occur in similar context tend to have similar meanings is the distributional hypothesis that we look according to the embeddings type here. So takes an example of king, queen and prince. When we convert that into a vector space, and with the vectors we will be able to get a similar directional vectors, and where we can relate it to each other. The king, queen and prince may have a related close similarity vector, and the same way the beverages where tea, coffee and milk will have the similar vector space. Now, how embeddings are learned? According to Word2Vec by Google, there are basically two methods. One is the continuous bag of words, where we will predict the word from the given context. The other type is skip-gram, where we will predict the context from the word. So, we will take the example of continuous bag of words. Consider the sentence, the cat sat on the mat. In the first training example, if we consider the and sat, it will predict cat. Now, how is the prediction happening according to the training example? It is using neural network, which we will be doing in the next few classes. In the second training example, suppose it is cat and on. The prediction is sat. The third, if it is sat and the prediction is mat. So, this is the way the continuous bag of words is being operated, and where it is can be used is when you have small data sets and faster training approach, and there are frequent words that are appearing, then this method can be used. The analogy is the fill in the blanks, where we would do as an exercise during our lower classes, where there are some blanks and that has to be filled. The other method is the skip-gram, where suppose we have the word of coffee, predict the surrounding words from the real corpus. Say for example, either it is cup of, morning, brew, espresso, it links to coffee. The other is drink, cough, hot, caffeine, coffee, bean. Using these words, either coffee can be predicted or given coffee, these words can be put in. So, this is skip-gram approach, and these can be used for rare words or large data sets, and where there is some accurate relationship has to be got. The analogy here is going to be given a word, what words closer to it can be predicted, whereas in continuous bag of words it was the fill in the blanks. So, in today's, coming to the end of the session, in today's class what we have seen is the cosine similarity, where we saw the relation between two documents in numeric form, and then combined cosine similarity with TF-IDF, which had some value to it, because in TF-IDF we removed the most common words that are not relevant, and cosine similarity captures the relation between any two documents. So, combining that two was an advantage, but the limitation there was again the semantic similarity or the syntactic similarity was not captured. So, we went into the embeddings type, and we saw just an introduction to embeddings with the basic two methods. One is continuous bag of words and another one is skip-gram. In the next session, we will be seeing how to do embedding using a neural network, and before moving into embeddings or the neural networks, we will have an introduction how a neuron works, and then we will get into the how embedding is done, and then from there we will move into the transformers. We will see you in the next class. Thank you.